is the amount of drug. Clearance, you can't see it?
Yeah, I can.
You need a minute?
We're just gonna have to find the question.
Oh, they're all mixed. Oh, shoot. I'm sorry. I didn't think about that. Darn it.
All right, I'm there.
Sorry. It's called definition of, well, you don't see that, I guess. Probably. Sorry about that. I should have thought about it. Didn't. Yeah. April 1st with a capital A and just the letter 1 or the number 1 with no space. Capital APRIL 1. Sorry, I mixed these up. I apologize. All right. Clearance is the amount of drug right there. It's not an amount of drug, is it? Well, I guess it is. It's the fraction of drug. Well, it's the amount, what is it? It's the amount of blood that can have all the drug removed per time. It's not, it's in liters per, it's in volume per time. It's not an amount, is it? And I think that's a really tricky concept. Clearance is not a rate. It's more like it's the blood flow that can have all the drug removed from it per time. So how would we change this to be true? Clearance is the amount of blood that can have all the drug removed from it per time. Okay, you'll get why that's false. You'd all get that right. Okay, next. This is the maximum organ clearance. I've got this one for number 2, the maximum clearance of any organ. Does that help? Yeah, I think it does. Maximum clearance of any organ is what? Clearance is equal to what? Q times E. E is limited because E is a percentage or a fraction, right? So E goes from 0 to 1. Clearance does not go from 0 to 1, does it? So if E is 1, which is the maximum that E can be, what is the maximum that clearance can be? Q, right? The maximum clearance can be is the blood flow to that organ. Q. So if you said Q or blood flow to the organ, you got that right. If you said anything else, you got that wrong. Does that make sense to everybody if you actually put math to it? Clearance is Q times E. We know E at the maximum can be only, it can't get bigger than 1, can it? You can't extract more than is there. So E is between 0 and 1. So if E is 1, then the maximum clearance can be is Q. All right. You good with that? Kind of. All right, next one. Drugs that are cleared by the liver that are low E drugs. So what does low E mean? It means it's our rusty dairy. It means clearance is determined by intrinsic clearance times fraction unbound. It means that FH is approaching what? 1. We say it's approximated by 1. Does that mean, though, if FH is approximated by 1, does that mean their F will be large? Means they could be. But what determines F? More things than just FH, right? What determines F? FA, FG, and FH. So it does mean if I asked you that it means it will always have a relatively large FH, then that would be true, wouldn't it? But does it dictate, that alone dictate that it's going to be a large bioavailability? No, because it could not be absorbed. Maybe the drug isn't even absorbed. Or maybe the drug gets wiped out by the P-glycoprotein or the enzymes in the gut wall. We don't know that. We don't have that piece of information. All we know is it'll make it through the liver pretty much intact. So could it have a bioavailability, high bioavailability? Absolutely. Does it always? Heck no. We don't have enough information, do we? Okay, is everybody good with that? That is a tricky one because you have to know two things. You have to know what a low EFH is, and you have to understand that F is more than just FH, right? Does that make sense to everybody? Questions about that one? Because I think that one's a tricky one. All right, Mr. Green Jeans. You guys probably don't know who Mr. Green Jeans is. Does anybody know what Captain Kangaroo is? See, I'm showing my age. Captain Kangaroo was a kid's show when I was a kid, and I loved Captain Kangaroo. I didn't care for Mr. Green Jeans, but anyway, Mr. Green Jeans is getting 400 milligrams Q12PO of drug Y, which is a high E drug, and it's PO. So right away, we're thinking, okay, we have to be on alert because this is a first pass, a high first pass drug. A lot of it will be eliminated as it goes through the liver. It's metabolized by CYP2D6 in the liver. So Mr. Green Jeans adds a drug which inhibits the activity of the CYP2D6. So it's a decrease in the intrinsic clearance. How will you change the dosing regimen to compensate? Well, what's going to happen to our CSS average? Oh, can I not? Wait. How do I? Right on this or not? Maybe not. All right, let me write over here then. So to see if we want to make a change in dose rate, we're going to look at our CSS average, right? Do we need to look at total in this case? When do we need to look at total? When do we not trust total? Or when do we need to look at free? When do we not trust total? If there's been a binding change. Has there been a binding change here? Not that we know of, right? It's an enzyme activity change. So we're fine with looking at total. So total, we gotta look at salt form, bioavailability, and dose rate, all over clearance. What do we know? We know our bioavailability is determined by FA, FG, and FH. And we know, in this case, we have a high extraction drug, so we've got our FH is determined by this, and our clearance is determined by this. So what's happened here? We've inhibited these enzymes. So we've got a decrease in intrinsic clearance. So what's going to happen to our FH here? It's going to increase, isn't it? More of that drug is going to make it through the liver because those enzymes have been inhibited. Does that make sense to everybody? Okay, so we'll see an increase in our CSS average, won't we? So what are we going to want to do? We're going to decrease our dose rate, aren't we? What about dose interval? Let's look at our half-life. What's going to happen to our half-life? Our half-life binding hasn't changed. Clearance is approximated by Q. Is intrinsic clearance going to be a property here that since our intrinsic clearance has changed, is that going to change our half-life? Nope, no change in dose interval. Tau. So we're going to leave our tau the same. So let's see, we're getting 400 Q12, so we're getting 800 a day. And we want to decrease our dose rate. So we're going to give 400 a day. and we're still gonna leave it every 12 hours. So this answer in here is wrong. It should be 200 milligrams every 12 hours. Right? Does that make sense to everybody? I think I corrected it on the quiz, but I may not have. I better go back and check. Is everybody able to think through that problem? All right, next one. Now your patient, Bob White, is getting 250 Q12PO of a drug H, which is a low extraction drug, which is metabolized by CYP3A4. Mr. White developed CHF, which decreases the blood flow, Q. How will you change the dosing regimen to compensate? Okay, he's getting 250 Q12. All right, so now we've got a low extraction drug. I'll come over and do this one on this board so everybody can see. So this is a low extraction drug given orally. What's happened is we have a decrease in Q, right? So for a low extraction drug, do we need to look at free concentration, or can we get away with looking at total? When do we need to look at free? When there's been everyone says binding change. Has there been a binding change? Not that we know of. We only know there's been a decrease in Q. So we can look at total. So what do we know about a low extraction drug? A low extraction drug clearance is determined by intrinsic clearance times binding. And for our bioavailability, we know it's FA times FG times FH, which for this kind of drug is approximated by 1. So will a decrease in Q affect CSS average? Nope. Nope. So no change in dose rate. How about dose interval? Let's take a look at half-life, 0.693 volume, over clearance. Will our half-life change? No. Do we need to make a change in tau? So we're going to keep our dose regimen the same, aren't we? Because it doesn't affect anything. Now, if it were a high extraction drug like over here, if we had a decrease in Q, that would be a different story, wouldn't it? Because Q is all over the place here. They actually cancel each other here, so there'd be no change in dose rate, but we'd see an increase in half-life, so we'd want to extend our interval and leave our dose rate the same, wouldn't we? Everybody good with that? So it really depends on whether it's a high or low extraction drug and what you're going to do, right? Which of the following are determinants of organ clearance? Well, organ clearance is Q times E, right? Q, so we know for sure that Q is it, right? What determines our E? Well, for a well-stirred jar model, it's intrinsic clearance and fraction unbound into plasma and Q. Does FA, FG, or FUT determine clearance? FA determines bioavailability, that's it. FG determines bioavailability, that's it. FU does, Q does, intrinsic clearance does. Tissue binding, the only thing that affects is our volume, right? Everybody good with that? questions? Is there a question? Are you guys confused about that? I click all of those and then go in and grade it separately because I don't want you guys to be told there's only 3 right answers out of those, so. No. Is FA determinative clearance? No, just determines bioavailability. FG? No, just determines bioavailability. FU, absolutely, yeah. Q, absolutely. Intrinsic clearance, absolutely. FUT? No, that determines volume. Right? Okay. Your patient is getting 500 milligrams Q12 of drug A. It's a low E drug, which is metabolized by CYP and given to your patient. You have a drug X inducer added. So it's a CYP2C9 inducer. So there's going to be an increase in intrinsic clearance. How will you need to change the dosing regimen to compensate? Okay, so we're going over to our low E side here. And instead of a decrease in Q, we've got a CYP inducer, right? So what's a CYP inducer going to do? Increase your intrinsic clearance, right? So if you're increasing your intrinsic clearance, you're going to see a decrease in your CSS average. Therefore, you're going to want to increase your dose rate, right? If you have an enzyme inducer, in both cases, we're increasing the clearance, right? With no other changes. So we're going to see a decrease in CSS average and a decrease in half-life. So we're going to want to decrease tau. Right? We're gonna have to give it more often. So what was he getting? 500 Q12. So he's getting 1,000 a day. And we're going to increase the dose rate to 2,000 milligrams per day. And the tau was 12 hours? Yeah, 12 hours. And we're going to decrease the tau to 6 hours, yes? So we're giving 4 doses a day. So 2,000 divided by 4 is 500 milligrams Q6, yes? Notice the dose stays the same, but obviously we've doubled the dose rate. That's why we don't want to get tied up in the dose when we're talking about things in general and making changes. So this one is, we got in a table of information, drug J, so it's the bottom one here. Exhibits what kind of clearance? Restrictive or non-restrictive clearance? Let's see. Well, how do we determine restrictive versus non-restrictive clearance? Well, we compare the E to the fraction unbound. How do we get an E out of this? Well, we know that it's totally cleared by the liver. How do we know that? The FE is 0. So 12.7 liters per hour. This is a low extraction drug, but what's the E? Well, it's 12.7 divided by 90, right? Did I skip too many steps, or are you okay with that? Where's my calculator? 12.7 divided by 90. The E is 0.14. And the fraction unbound is 0.2. So is this restrictive or non-restrictive? It's restrictive, right? There's the percent extracted is less than that is free. Do you know how I got the 0.14? remember the clearance of any drug is Q times E. If we know the clearance is, what is it, 12.7 liters per hour? And we assume, we assume a normal Q of 90 liters per hour. We can solve for E, 12.7 divided by 90. So 14% of the drug is being changed as it goes to the liver, right? And how much was free and available for that? 20%. So E at 0.2, or I'm sorry, E at 0.14 is less than or equal to the fraction unbound, which is 0.2, right? 20% was free and 14% was being eliminated. So it is limited or restricted to only free drug. You could have also seen it as a low E drug, and all low E drugs are restricted with clear. You could have skipped the math, actually, probably. Good? Questions? Well, we could go back too and look at, if you look at drug H here, could we answer this for drug H? For drug H, the clearance is 72. 72 liters per hour. So what's the E there? Can someone do the math for me quick? Anybody get it? 0.8. So 80% of it's being eliminated as it goes through the liver. So in this case, E is greater than what's free. Only 15% is free, right? So it doesn't care whether it's free or bound, does it? So this is non-restricted. Everybody good with this idea? Your patient on drug J. So drug J is the same one we just talked about. Has an increase in AAG due to surgery. Okay, it has an increase in AAG because of surgery. So what's happening? The AAG has increased. What is AAG? An important binding protein. So this is a low E drug. So I'm going to go over to this side, to our low E side. And what's happened here? We've got an increase in AAG. So if we have an increase in AAG, what does that mean? What does that mean? What's happening? It's a major binding protein, right? If we've increased the amount of binding protein and the drug is bound to that, what's going to happen to our binding? It's going to increase, right? So what's going to happen to our fraction unbound? It's going to decrease, right? So now, do we need to look at free concentration? Do we need to look at free concentration? When do we need to look at free concentration? If there's been a, and has there? Yeah, so we got to look at free, don't we? So we're going to multiply this whole mess times fraction unbound, aren't we? To get our free concentration. So what's happened here? What's happened here is a decrease in fraction unbound. So that's going to decrease our clearance, but it also decreases the peripheral fraction unbound at steady state. those will balance out, won't they? And we need no change in dose rate. How about dose interval? Well, we're gonna have a decrease in our volume. We're also gonna have a decrease in our clearance. Again, that will balance each other out at steady state, and we're gonna need no change in tau. So we would recommend no changes here. But what's gonna happen to the total concentration? The total concentration is gonna go up, isn't it? Because clearance is gonna go down. So the team is gonna wanna decrease the dose rate. And you're gonna say, whoa, Nelly. At steady state, it should balance out. That's a very tricky one, isn't it? Any questions on that before I move on? That's a pretty tricky one. We have to look at free when there's been a binding change. You should also know what happens to total so that you can anticipate what people are going to want to do when they see that total concentration come back from the lab. Total concentrations at steady state can be used to determine what is happening with free concentrations as long as the drug is being given IV. Well, no, it doesn't matter about that, does it? Well, how would we change this to be true? Total concentrations can be used to determine what's happening with free concentrations at steady state as long as there's no change in binding. Right? All right, let's take a quick break and then we're going to start renal. Woohoo! All right. So there's your review. And we'll talk about that when you get back. Let's just take a 5-minute break and then we'll get into it.
You look like an egg down the station.
What'd I just do?
Sorry, the door.